Is there a limit to human scientific understanding? At first, that question can sound abstract, as if it belongs to philosophy more than to the physical world. But it begins somewhere very simple, in moments so ordinary they are easy to overlook. It begins when someone notices that the sun rises in roughly the same place each morning, when shadows change length across the day, when certain stars return to the same positions each year. Long before equations or laboratories, scientific understanding began as a quiet habit of attention. Patterns were noticed because they mattered. They helped people anticipate what would happen next. They offered a small sense of stability inside a world that otherwise felt unpredictable. From the very beginning, then, scientific understanding was not about completeness. It was about orientation. It was a way of finding one's footing in reality, of learning which features of the world could be relied upon and which could not. Understanding did not mean knowing everything. It meant knowing enough to move forward with a little more confidence than before. That humble origin still shapes science today, even when it reaches into realms far removed from everyday experience. If you find yourself drawn to these slow, careful explorations, a gentle like or a quiet subscribe helps keep them possible. And it's always grounding to know where these thoughts are being heard, whether it's late at night or early in the morning, somewhere familiar or far away. To ask whether there is a limit to human scientific understanding, it helps to first be clear about what scientific understanding actually is. It is not a warehouse of facts waiting to be filled to capacity. It is a process, one that unfolds over time, shaped by questions, observations, and revisions. Scientific understanding lives in the relationship between the world and the models we build to make sense of it. It grows when those models allow us to explain what we see and anticipate what we have not yet seen. This means scientific understanding is always provisional. A theory is not a final answer. It is a tool that works within a certain range of conditions. Newton's laws describe the motion of planets and falling apples with extraordinary accuracy, but they are not wrong when they fail near the speed of light or inside black holes. They are simply incomplete. They remain useful where they apply, even as deeper theories extend beyond them. Understanding, in this sense, is layered rather than replaced. This layered structure is one of the quiet strengths of science. New knowledge does not usually erase old knowledge. It reframes it. Each layer reveals where previous assumptions held and where they quietly gave way. Scientific understanding grows not by racing toward a final picture, but by learning where each picture fits and where it does not. Because of this, the idea of a limit to scientific understanding is not immediately obvious. If understanding is always partial and always revisable, then perhaps it can deepen indefinitely. Perhaps there is always another layer to uncover, another refinement to make, another connection to notice. The question becomes not whether science will finish, but whether there are features of reality that resist understanding altogether. To approach that question gently, it helps to notice how science actually progresses. Scientific understanding advances through observation, but observation itself is never passive. To observe is to interact. Light must scatter off an object and enter an eye or a detector. A particle must leave a trace in a chamber. A signal must be amplified, filtered, and recorded. Every observation is a physical event, shaped by the tools used to make it. Those tools are extensions of human senses. Telescopes extend vision. Microphones extend hearing. Particle detectors extend touch into realms far smaller than skin could ever feel. But no matter how sophisticated they become, instruments remain physical objects governed by the same laws as the phenomena they measure. This means scientific understanding is inseparable from the means by which evidence is gathered. This is where the idea of limits first begins to take shape, not as an abrupt wall, but as a gradual narrowing. Instruments have finite precision. Measurements are always accompanied by uncertainty. Noise, interference, and background effects never vanish completely. They can be reduced, but they cannot be eliminated. Scientific understanding, therefore, does not deal in absolute certainty. It deals in confidence ranges, probabilities, and error bars. Rather than weakening science, this has made it stronger. By acknowledging uncertainty, science learns where its conclusions are robust and where they are fragile. Understanding deepens not by pretending uncertainty does not exist, but by mapping it carefully. In this way, uncertainty becomes part of what is understood. Still, there are moments when uncertainty does more than blur the edges. In modern physics, it enters the core of how reality behaves. Quantum mechanics revealed that certain pairs of properties cannot be known simultaneously with arbitrary precision. This is not a limitation of instruments, but a feature of nature itself. The act of measuring one quantity unavoidably disturbs another. Scientific understanding here does not eliminate uncertainty. It explains why uncertainty is unavoidable. This kind of discovery subtly shifts the meaning of a limit. A limit is no longer something that better technology will eventually overcome. It becomes something woven into the fabric of reality. Scientific understanding can explain the existence of such limits, even if it cannot bypass them. In doing so, it gains depth without gaining total control. There is a similar shift when science confronts scale. Some phenomena unfold over time scales far longer than a human life. Others occur at energies or distances that can only be probed indirectly. We cannot watch a galaxy form in real time, nor can we peer directly into the first moments after the universe began. Yet, scientific understanding still reaches these domains through inference, through traces left behind, through patterns imprinted in radiation and structure. This reveals another important feature of scientific understanding. It does not require direct access to everything it seeks to explain. It relies on consistency, coherence, and explanatory power. If a model successfully explains many independent observations with a small set of principles, confidence grows, even when some aspects remain inaccessible. However, inference has its own boundaries. Conclusions drawn indirectly depend on assumptions about what remains unseen. When those assumptions are wrong, understanding must be revised. This does not mean inference is unreliable, it means it is conditional. Scientific understanding always rests on a foundation that can, in principle, shift. As science advances, it often encounters phenomena that are not merely complicated, but complex. In complex systems, small changes can lead to large and unpredictable outcomes. Weather, ecosystems, and many biological processes fall into this category. Even when the underlying physical laws are known, prediction becomes difficult beyond a certain horizon. This introduces a distinction that becomes increasingly important. Understanding a system is not the same as being able to predict it in detail. Science can explain why a system behaves unpredictably. It can identify the mechanisms that amplify small uncertainties, but it cannot always forecast exact outcomes far into the future. Here again, a limit appears, not in explanation, but in foresight. These kinds of limits accumulate quietly. None of them declare an end to understanding. Instead, they shape its character. Scientific understanding becomes less about domination and more about navigation. It tells us where we can rely on predictions, where we must accept variability, and where uncertainty is intrinsic. The idea of a final ceiling, then, becomes less straightforward. If understanding is defined as the ability to build ever more accurate and comprehensive models, perhaps it can continue deepening without bound. But if understanding is defined as complete knowledge of all details, at all times, then the structure of the universe itself begins to matter. The universe has a finite age and a finite speed at which information travels. This means there are regions of space whose signals have not yet reached us, and regions that never will. Scientific understanding is limited not by curiosity, but by causality. One cannot learn about what has never interacted with one's past light cone. This is not a temporary obstacle. It is a consequence of spacetime geometry. Yet, even here, understanding does not simply stop. Cosmology has learned to speak carefully about what lies beyond observation, distinguishing between what is known, what is inferred, and what remains open. Scientific understanding includes these distinctions as part of its content. Knowing where knowledge ends is itself a form of knowledge. As the question of limits becomes more refined, it also becomes less dramatic. A limit does not necessarily mean an end point where progress halts. It can mean a boundary that understanding approaches asymptotically, learning more about its shape without ever crossing it. Many physical theories behave this way, becoming increasingly precise without becoming complete in an absolute sense. This brings the question back to a more human scale. Scientific understanding is a collective process unfolding across generations. No single mind contains it. It lives in books, datasets, instruments, and shared practices. Its growth depends not only on nature, but on communication, education, and collaboration. Understanding deepens because it is distributed. This distribution allows science to advance far beyond the limits of individual cognition. But it also introduces new kinds of constraints. As knowledge expands, specialization increases. No one person can hold the entire structure in mind. Understanding becomes fragmented, coordinated through institutions rather than intuition. This does not impose a fundamental limit, but it changes the experience of understanding. At this early stage of the question, one thing becomes clear. Asking whether there is a limit to human scientific understanding is not the same as asking whether science will fail or stop. It is asking about the shape of understanding itself. Is it a path that leads to a final plateau, or a landscape that continues to open into new terrain, even as certain horizons remain fixed? The answer cannot be reached all at once. It requires tracing how understanding emerges, how it grows, how it encounters resistance, and how it adapts. It requires staying close to the physics, the methods, and the real constraints that shape what science can do. From here, the path leads naturally backward before it moves forward, toward the origins of scientific thinking and human experience. By understanding how science began and why it took the shape it did, the question of its limits becomes less abstract and more grounded, anchored in the same curiosity that first looked up at the sky and wondered what patterns might be trusted. Long before science became formal, before it had names, instruments, or institutions, it emerged from a much quieter source. It arose from living bodies moving through an environment that rewarded attention. Early human understanding did not begin with a desire to explain the universe. It began with a need to survive within it. Food had to be found. Seasons had to be anticipated. Dangers had to be recognized quickly. Understanding started as an extension of perception, shaped by what mattered most. In this early form, understanding was inseparable from the body. The rhythm of walking, the arc of a thrown stone, the eye cycle of hunger and rest all created an intuitive sense of cause and effect. When certain actions reliably led to certain outcomes, those patterns were remembered. Over time, memory itself became a tool, storing fragments of experience that could be compared and combined. Understanding was not abstract. It was practical, grounded, and deeply local. As groups grew and language developed, these patterns began to be shared. A successful hunt, a dangerous plant, a predictable flood, each became something that could be described and passed on. This sharing marked a quiet turning point. Understanding was no longer limited to what one person had directly experienced. It could accumulate across individuals and across time. Knowledge began to outlast the moment that produced it. Counting emerged in much the same way. At first, numbers were not ideas. They were comparisons. More than before, less than yesterday. Enough for the winter. Over time, counting became more precise, and precision opened new possibilities. Herds could be managed. Trade could be coordinated. Cycles could be tracked. The sky itself became a kind of calendar, with repeating patterns that aligned with events on the ground. This is where early scientific understanding took its first recognizable shape. The world was no longer just reacted to. It was observed with expectation. If the stars returned to certain positions, something familiar would follow. If shadows shortened or lengthened in a particular way, time could be inferred. These patterns were not yet explained, but they were trusted. Understanding grew not by knowing why, but by knowing when. What matters here is that scientific understanding did not begin with a search for ultimate truth. It began with reliable regularities. The earliest models of the world were not theories in the modern sense. They were habits of expectation. When those expectations held, confidence grew. When they failed, attention sharpened. Curiosity was trained by surprise. Over generations, this process refined itself. Tools extended perception. Marks on bone or stone preserved counts. Simple geometries emerged from land measurement and construction. Each step added a layer of abstraction, but always in service of something concrete. Scientific understanding was never separate from use. It earned its place by working. This practical grounding shaped the way science developed. Early explanations often took the form of stories, not because people were careless with truth, but because stories were effective containers for pattern and causation. A story links events in time. It explains why something happens next. In this sense, myth and early science were not opposites. They were different ways of organizing experience before precise measurement became possible. As tools improved, stories gradually gave way to more constrained descriptions. Measurement introduced discipline. A shadow was not just long or short, but a specific length at a specific time. A year was not just a cycle, but a countable interval. Precision began to separate what could be trusted from what merely felt plausible. This shift was subtle but profound. Scientific understanding began to detach from immediate human experience. It reached toward phenomena that could not be sensed directly, only inferred. The phases of the moon could be mapped. The motion of planets could be predicted. Regularities that spanned years or lifetimes could be captured in records and calculations. Still, these advances remained anchored in human scale. Early science worked best where patterns were stable and repetition was visible. It thrived in astronomy, agriculture, and mechanics because these domains offered consistency. Where variability dominated, understanding lagged. This is not because early thinkers lacked intelligence, but because understanding depends on structure in the world as much as effort in the mind. This dependence is crucial. Scientific understanding does not arise solely from human ingenuity. It arises from an interaction between minds and a world that is patterned enough to be understood. Where patterns are sparse or fragile, understanding grows slowly. Where patterns are strong and persistent, understanding accelerates. As science became more formal, this interaction sharpened. Observation was no longer casual. It was organized. Experiments were designed to isolate causes. Variables were controlled. The goal shifted from noticing patterns to testing them. A claim was no longer accepted because it fit experience, but because it survived deliberate attempts to disprove it. This methodological shift did not remove science from its human roots. It refined them. Curiosity became disciplined. Skepticism became productive. Understanding advanced not by accumulating beliefs, but by pruning them. The willingness to let ideas fail became as important as the ability to imagine them. Here, the question of limits begins to appear again in a gentler form. Scientific understanding grows through interaction with the world, but that interaction is selective. Questions are chosen. Experiments are feasible or not. Some phenomena lend themselves to isolation and repetition. Others resist it. Understanding does not expand uniformly in all directions. It follows paths where evidence can be gathered reliably. This means that the growth of scientific understanding has always been shaped by what can be practically engaged. Early science flourished where the world offered stable, repeatable signals. As tools improved, those signals expanded into new domains. But the dependence remains. Understanding follows access. This historical path reveals something important about limits. Limits are not always encountered as barriers. Often they appear as gradients. Some questions yield easily to inquiry. Others respond slowly. Some may never respond at all, not because they are meaningless, but because the universe does not present them in a way that allows sustained interaction. From this perspective, asking whether there is a limit to human scientific understanding is not asking whether curiosity will run out. It is asking whether the world will always continue to offer patterns that can be reliably engaged, measured, and tested. It is asking whether the partnership between mind and nature has an inherent boundary. As science moved beyond direct human scale, into realms of the very small and the very large, this partnership became more delicate. Instruments replaced senses. Models replaced intuition. Understanding increasingly depended on layers of mediation. Each layer added power, but also distance. Yet even here, the same principle holds. Scientific understanding grows when the world responds consistently to careful questioning. Where it does, understanding deepens. Where it does not, uncertainty remains. This is not a failure of science. It is a reflection of the relationship it has always had with reality. By tracing scientific understanding back to its origins in everyday human experience, something becomes clear. science did not begin with the ambition to know everything. It began with the need to know enough. Its strength has always come from aligning curiosity with what the world is willing to reveal. From here, the question of limits becomes more precise. To ask whether scientific understanding has an end is to ask how far this alignment can extend. Can methods born from survival and refined through measurement continue to illuminate ever more abstract layers of reality? Or will there come a point where the world's structure no longer offers stable footholds for understanding to grip? That question does not emerge from speculation. It emerges naturally from the history of how science has grown so far. As scientific understanding matured, it began to rely less on direct familiarity with the world and more on something quieter and more powerful. It began to rely on models. A model is not the thing itself. It is a simplified representation, a way of capturing certain features of reality while deliberately ignoring others. This shift marked a subtle turning point because it changed what understanding meant. To understand something scientifically was no longer to experience it directly, but to describe its behavior through an abstract structure that could be tested and shared. This move toward modeling did not happen all at once. It emerged naturally from the need to make sense of patterns that were too complex, too distant, or too slow to grasp intuitively. The motion of planets, for example, could not be understood by watching the sky alone. Their paths unfolded over months and years. By drawing diagrams, recording positions, and eventually expressing relationships mathematically, early astronomers created models that could compress long spans of time into a single, coherent picture. What made these models powerful was not their realism, but their restraint. A good model does not attempt to capture every detail. It focuses on what matters for a particular question. Air resistance can be ignored when predicting the fall of a stone over a short distance. The texture of a planet's surface can be ignored when calculating its orbit. Understanding grows not by including everything, but by choosing carefully what to leave out. This selectivity is not a flaw. It is the core mechanism by which scientific understanding advances. By stripping away complexity, models reveal structure. They expose relationships that would otherwise be hidden beneath noise and detail. But this strength carries a consequence. Every model has a domain of validity. Outside that domain, its predictions degrade. Understanding is always conditional. This conditional nature of understanding often remains invisible when models work well. When predictions match observations repeatedly, confidence builds, and the model begins to feel like a faithful portrait of reality. But history shows that this feeling can be misleading. Scientific progress is filled with moments when successful models were later revealed to be approximations of something deeper. The motion of objects was once understood entirely through everyday intuition and classical mechanics. These models worked extraordinarily well at human scales. But as measurements became more precise and speeds increased, small discrepancies appeared. Eventually, those discrepancies forced a revision of the underlying model, leading to relativity and quantum mechanics. The old models did not vanish. They found their place within a broader framework. This pattern reveals an important feature of scientific understanding. It grows by nesting models within models. Each layer captures reality at a certain resolution. Deeper layers do not erase the shallower ones. They explain why they work where they do and why they fail where they must. Understanding becomes a hierarchy rather than a single, final picture. Because of this, scientific understanding is never absolute. It is always tied to scale, context, and purpose. A model that explains atomic behavior is not useful for predicting weather. A model that captures climate trends cannot tell you whether it will rain tomorrow afternoon. Understanding deepens by diversifying, not by converging on a single all-encompassing description. This diversification raises an important question about limits. If understanding is always mediated by models, and models always simplify, then there may be aspects of reality that resist modeling altogether. Not because they are mysterious, but because they do not present stable patterns that can be abstracted cleanly. Some systems change too quickly. Others depend sensitively on initial conditions that cannot be measured with sufficient precision. Still others involve interactions so numerous that tracking them individually becomes impractical. In these cases, scientific understanding often shifts its goal. Instead of predicting exact outcomes, it seeks statistical regularities, average behaviors, or qualitative insights. This shift does not represent a retreat. It represents an adaptation. Understanding adjusts to what the system allows. Where exact prediction is impossible, explanation may still be possible. Where explanation becomes difficult, classification or description may still offer insight. Scientific understanding is flexible, but that flexibility is itself shaped by constraints. The reliance on models also introduces an important separation between understanding and truth. Models can be useful even when they are known to be false in detail. A map that distorts distances can still guide a journey. A simplified equation can still reveal a trend. Scientific understanding often advances by using tools that are explicitly acknowledged to be incomplete. This pragmatic approach is one of science's quiet strengths. It allows understanding to grow even in the presence of imperfection. But it also means that scientific knowledge is never final. Every model carries the possibility of revision. Every explanation is provisional, waiting to be tested under new conditions. As models become more abstract, the gap between intuition and understanding widens. Many modern scientific theories describe phenomena that cannot be visualized directly. They rely on mathematics, probability, and indirect inference. This does not mean they are disconnected from reality. It means reality itself does not always align with human intuition. Here, the question of limits becomes sharper. If understanding depends on models that grow increasingly abstract, is there a point where abstraction becomes too detached to be meaningful? Is there a level of description where models no longer connect to observation in a reliable way? Science navigates this tension by insisting on empirical grounding. No matter how abstract a model becomes, it must ultimately connect back to measurement. Predictions must be testable. Explanations must correspond to observable consequences. This requirement anchors understanding, but it also constrains it. Some ideas remain speculative because they cannot yet be tested. Others may remain forever beyond empirical reach. This is not a failure of imagination. It is a reflection of the structure of scientific understanding itself. Models are bridges between thought and world. Where the gap becomes too wide, the bridge cannot be built. Still, it is important to notice that the limits encountered here are not absolute barriers. They are thresholds. Scientific understanding often advances by finding new ways to test old ideas, or by discovering new phenomena that make previously inaccessible questions approachable. Limits shift as methods evolve. Yet the reliance on models ensures that understanding will always be partial. There will always be aspects of reality that lie outside the frame of any given representation. To understand scientifically is not to possess reality, but to engage with it through carefully chosen lenses. By recognizing this, the question of whether scientific understanding has a limit becomes less about an endpoint and more about a pattern. Understanding grows by approximation. It advances through refinement, not completion. It becomes more reliable in some domains while remaining uncertain in others. From this perspective, the possibility of a final, complete understanding begins to feel less natural. Not because the universe is inscrutable, but because understanding itself is a process shaped by simplification, selection, and context. It is powerful precisely because it does not try to be everything at once. As scientific understanding moves forward, it carries this structure with it. Models become more sophisticated, but they do not escape their role as models. The question then is not whether science can eliminate this limitation, but how it responds to it. From here, the path leads naturally to the act that connects models back to the world itself. Measurement. It is through measurement that models are tested, refined, or abandoned. And it is through measurement that some of the most profound limits on scientific understanding quietly reveal themselves. Measurement is the moment where scientific understanding touches the world directly. It is where abstract ideas are forced to answer to physical reality. A model may be elegant, consistent, and internally convincing, but without measurement it remains ungrounded. Measurement is how nature responds to our questions, and those responses are never given freely. They must be extracted through interaction. To measure something is not simply to look at it. It is to intervene. Light must strike an object and scatter back. A probe must disturb a system to register its state. A detector must absorb energy to record a signal. Every measurement is an exchange, and that exchange has consequences. The world is not observed from a distance. It is engaged. This engagement is where scientific understanding gains its authority, but it is also where its limits begin to appear with clarity. Instruments are not neutral windows. They have sensitivities, thresholds, and biases. They respond differently depending on conditions. They are affected by temperature, noise, vibration, and interference. Even the most carefully designed experiment sits within an environment that cannot be completely controlled. Early measurement relied on human senses, extended only slightly by simple tools. Lengths were compared against rods. Time was tracked by shadows or flowing water. These methods were coarse, but they were sufficient to reveal regularities. As science progressed, the demand for precision increased. More subtle effects required more refined instruments. Each gain in precision revealed new layers of complexity. Precision, however, is never free. To measure more accurately, one must invest more energy, time, and care. Signals must be amplified. Background noise must be reduced. Experiments must be repeated. Errors must be analyzed. Scientific understanding advances not just through insight, but through patience and discipline. This leads to a crucial realization. Measurement does not converge effortlessly toward perfect knowledge. It asymptotically approaches it. Each improvement yields diminishing returns. At some point, increasing precision requires disproportionate effort for marginal gains. This is not an economic inconvenience. It reflects physical reality. Nature does not offer infinite clarity. Uncertainty is therefore not a temporary defect in scientific understanding. It is a permanent feature. Every measurement carries an error margin, not because scientists are careless, but because measurement itself is constrained. There are limits to how finely quantities can be resolved, how well variables can be isolated, and how completely systems can be shielded from external influence. In classical physics, uncertainty was often treated as a practical issue. Better instruments would eventually resolve it. But the development of quantum mechanics revealed a deeper layer. At small scales, uncertainty is not just about imperfect tools. It is woven into how physical properties exist. Certain quantities do not have precise values simultaneously. Measuring one necessarily disturbs the other. This discovery reshaped scientific understanding. It showed that the act of measurement is not merely revealing reality, but participating in its unfolding. The properties observed depend on how they are observed. This does not make science subjective. It makes it relational. Understanding becomes a description of interactions rather than a catalog of intrinsic attributes. Even outside the quantum realm, similar issues arise. Measuring complex systems often alters their behavior. In biology, observation can stress organisms. In social systems, measurement can change outcomes. In climate science, the system under study evolves while it is being measured. Scientific understanding must account for this reflexivity. As a result, science has learned to be cautious about what measurement can deliver. It distinguishes between what is measured directly and what is inferred. It develops statistical tools to separate signal from noise. It builds redundancy into experiments to guard against hidden biases. Understanding grows not by ignoring uncertainty, but by embracing it methodically. Yet there are cases where uncertainty does more than blur results. In chaotic systems, tiny uncertainties grow rapidly over time. Weather is the classic example. The equations governing atmospheric motion are well known, but small differences in initial conditions lead to diverging outcomes. Measurement limits here translate directly into prediction limits. This does not mean weather is incomprehensible. It means there is a horizon beyond which detailed forecasts lose reliability. Scientific understanding adapts by shifting focus. Instead of predicting exact states far into the future, it predicts probabilities, trends, and patterns. It learns what can be said confidently and what cannot. This adaptive response reveals an important feature of scientific understanding. Limits do not simply block progress, they redirect it. When exact knowledge is unavailable, science seeks approximate knowledge. When precise prediction fails, it seeks explanatory frameworks. Understanding remains active, but its form changes. Measurement also introduces limits through scale. Some quantities are too small, too large, too fast, or too slow to measure directly. The interiors of stars, the earliest moments of the universe, and the behavior of individual particles at extreme energies are all beyond direct observation. Scientific understanding in these domains relies on indirect evidence, models, and consistency across multiple lines of inquiry. This indirectness does not weaken understanding, but it does constrain it. Inferences depend on assumptions. Those assumptions must be tested where possible, but some may remain untested indefinitely. Understanding becomes layered, with confidence varying across domains. At this stage, the question of limits takes on a clearer shape. Scientific understanding is not bounded by ignorance alone. It is bounded by the structure of interaction between observer and world. Measurement is the channel through which understanding flows, and that channel has a finite capacity. This does not imply that scientific understanding will suddenly stop. It implies that its growth is shaped. Certain kinds of questions yield precise answers. Others yield probabilistic ones. Still, others may resist quantification altogether. Science learns to recognize these distinctions and to respect them. The presence of limits in measurement also encourages creativity. New instruments open new windows. New methods extract signals from noise. Entire fields have emerged from the ability to measure what was once invisible. Limits that once seemed fundamental have often been pushed back through ingenuity. But each breakthrough also reveals new boundaries. As understanding deepens, it encounters subtler effects and finer constraints. The process repeats. Measurement refines understanding, and understanding exposes the limits of measurement. This ongoing interplay suggests that limits are not external obstacles placed in the path of science. They are part of its terrain. To understand scientifically is to navigate between what can be measured, what can be inferred, and what remains uncertain. From here, the question of a limit to scientific understanding becomes more grounded. It is no longer about whether knowledge will run out, but about how the universe responds to inquiry at its deepest levels. To explore that, the next step is to examine what happens when science encounters limits that arise not from complexity or noise, but from the fundamental laws governing reality itself. At a certain point, the limits revealed by measurement stop looking like practical challenges and start looking like messages about the structure of reality itself. They are not signals that science has failed to ask the right questions. They are signals that the universe answers some questions only in particular ways. To understand whether human scientific understanding has a limit, it becomes necessary to listen carefully to what those answers imply. One of the clearest examples comes from quantum mechanics, which did not emerge from philosophical speculation, but from careful experiments that refused to behave as expected. When scientists began probing matter at very small scales, they found that familiar ideas about position, motion, and causality no longer applied cleanly. Particles did not behave like tiny objects following well-defined paths. Instead, their behavior was described by probabilities, by distributions of possible outcomes rather than single, definite trajectories. At first, this uncertainty was tempting to treat as a technical problem. Perhaps instruments were too crude. Perhaps hidden variables were waiting to be discovered. But over time, experiments became more refined, and the uncertainty remained. It became clear that this was not a gap in knowledge waiting to be filled. It was a feature of how physical properties exist. In quantum mechanics, certain pairs of quantities cannot both be sharply defined at the same time. This is not because nature is fuzzy, but because the concepts themselves lose their independence at small scales. Position and momentum, for example, are not separate attributes that can be pinned down simultaneously. The act of measuring one reshapes the conditions under which the other can be defined. Scientific understanding responded by changing its language. Instead of describing what is, it began describing what is likely. Instead of trajectories, it used wave functions. Instead of certainty, it used statistical structure. This was not a retreat from understanding. It was an expansion of it, an acknowledgement that the universe does not always offer the kind of answers intuition expects. What matters here is not the mathematics, but the implication. scientific understanding discovered a domain where complete precision is not merely unavailable, but meaningless. The limit was not imposed by ignorance. It was imposed by the nature of physical reality. Understanding deepened by learning where definiteness itself dissolves. A similar shift occurred with the development of relativity, which redefined how space and time are related. Before relativity, it was natural to assume that time flowed uniformly everywhere, that events could be labeled as simultaneous or sequential in an absolute sense. Relativity revealed that this assumption does not hold. Measurements of time and distance depend on motion and gravity. There is no universal clock ticking in the background of the cosmos. This has profound consequences for scientific understanding. It means that descriptions of reality are always situated. Observers in different states of motion do not merely perceive different versions of the same events. They inhabit different slices of space-time. There is no single global perspective from which all events can be ordered absolutely. Once again, this is not a limitation of instruments or intelligence. It is a property of space-time itself. Understanding does not collapse under this realization. It adapts. Physics learns to describe invariant relationships, quantities that remain consistent even as perspectives shift. But the price of this adaptation is the loss of absolute simultaneity and absolute order. Relativity also introduces horizons. Because signals travel at a finite speed, there are regions of the universe that cannot influence one another. As the universe expands, some regions recede faster than light can bridge the gap. Events beyond those horizons are not just unobserved, they are unobservable in principle. No experiment, no signal, no amount of patience can bring information from those regions into causal contact. Scientific understanding can describe these horizons. It can calculate where they lie and how they evolve, but it cannot cross them. Knowledge here reaches a boundary set by the geometry of space-time. Understanding includes the recognition of what cannot be accessed. Thermodynamics introduces a different kind of limit, one tied to time and irreversibility. The laws governing energy and entropy describe a universe in which certain processes are overwhelmingly likely and others are overwhelmingly unlikely. Order tends to disperse. Energy gradients flatten. Information, once scrambled, is difficult to reconstruct. This has implications for scientific understanding that are easy to overlook. Memory, measurement, and computation all require physical systems that maintain order against entropy. Recording data, storing knowledge, and performing calculations all generate heat. Understanding has a thermodynamic cost. Because of this, scientific understanding cannot grow without constraint. It must operate within an energy budget. It must dissipate entropy into its environment. While these costs are often negligible at small scales, they become significant when understanding is extended over large systems or long times. Thermodynamics also gives time a direction. While many fundamental equations are symmetric with respect to time, the macroscopic world is not. Causes precede effects. Records exist of the past, not the future. This asymmetry shapes what can be known. Scientific understanding can reconstruct past events from traces left behind, but it cannot access future events in the same way. This distinction matters deeply. It means that understanding is always retrospective to some degree. Even prediction relies on extrapolation from the present, constrained by uncertainty and entropy. The future is not hidden simply because it has not happened yet. It is hidden because the universe does not preserve information about it in advance. Taken together, these discoveries reveal a pattern. As science penetrates deeper into reality, it does not find a smooth path toward total clarity. It finds structure, but also boundaries. These boundaries are not obstacles to be removed. They are features to be understood. Quantum mechanics shows that some properties cannot be jointly defined. Relativity shows that some perspectives cannot be unified. Thermodynamics shows that some processes cannot be reversed. In each case, scientific understanding grows by explaining why the limit exists, not by transcending it. This reframes the idea of a limit to scientific understanding. A limit does not necessarily mean an end to inquiry. It can mean a transition from seeking complete description to seeking principled explanation. Understanding becomes deeper even as certain ambitions are relinquished. Importantly, these limits do not accumulate into a single, final barrier. They are distributed across domains. Each arises from a different aspect of physical law. Together, they suggest that the universe does not present itself as a fully transparent object to be known exhaustively. It presents itself as a system with internal constraints that shape how knowledge can form. Scientific understanding, then, is not marching toward a final unveiling. It is learning the contours of what unveiling means. It discovers not only how things behave, but why certain kinds of knowledge are unavailable. This realization does not diminish science. It stabilizes it. It replaces the idea of limitless conquest with the idea of informed navigation. Understanding becomes less about capturing reality in full, and more about aligning with the ways reality allows itself to be described. From here, the question of limits naturally expands outward. If the fundamental laws of physics impose boundaries on precision, perspective, and reversibility, what happens when scientific understanding confronts extremes of scale? What happens when it stretches from the smallest particles to the largest structures in the universe? That is where the next stage of the question quietly leads. When scientific understanding moves outward to confront extremes of scale, it encounters limits that feel different from those revealed by measurement or fundamental law. These are not limits of precision or principle, but limits of access. The universe is vast, and it is old, and scientific understanding must work within both of those facts at once. At the smallest scales, science probes distances far beyond direct experience. Particles smaller than atoms are not observed as objects, but as events, traces, and interactions. Understanding here relies on indirect signatures, on patterns in detector readouts, on statistical regularities emerging from many repetitions. The smaller the scale, the more energy is required to probe it, and the more violent the interaction becomes. At some point, attempting to see more detail begins to destroy the very structures being investigated. This creates a subtle boundary. Scientific understanding can describe what happens when particles interact at high energies, but it cannot always preserve the identity of what it is probing. The act of inquiry becomes inseparable from transformation. Understanding survives by shifting focus from objects to processes, from things to interactions. At the opposite extreme, scientific understanding faces the immensity of cosmic scale. Galaxies are separated by distances so large that light takes millions or billions of years to cross them. What is observed in the sky is not the universe as it is now, but the universe as it was when that light began its journey. Understanding the cosmos therefore requires reconstructing a history from delayed signals, assembling a coherent picture from fragments arriving out of sequence. This temporal separation places a natural constraint on understanding. The further away an object is, the older the information it provides. At great distances, this information approaches the earliest eras of the universe itself. Beyond that point, there is nothing to observe directly, because no light has had time to reach us. Scientific understanding can infer what happened earlier through theory and indirect evidence, but it cannot watch those moments unfold. This introduces the idea of the observable universe, a region defined not by physical boundaries, but by time and light. Beyond it may lie more universe, perhaps much more, but it is causally disconnected from us. Scientific understanding can describe this possibility, but it cannot test it directly. Knowledge here becomes conditional, framed carefully around what is accessible. As the universe expands, this situation becomes more pronounced. Distant galaxies are carried away by the expansion of space itself. Some are receding so rapidly that their light will never reach us, no matter how long we wait. Information is not just delayed, it is permanently lost to observation. Scientific understanding must accept that some aspects of reality will remain forever beyond empirical reach. This does not halt cosmology, it reshapes it. Understanding shifts from cataloging every region to studying the statistical properties of what can be seen. Large-scale structure, background radiation, and universal constants become the focus. The goal is no longer to map everything, but to understand the rules that govern everything we can observe. Scale also introduces limits through rarity. Some phenomena occur so infrequently that direct observation becomes impractical. The formation of the first stars, the merging of supermassive black holes, or the decay of extremely long-lived particles may happen on timescales or in conditions that cannot be reproduced easily. Scientific understanding relies on patience, on inference, and on rare signals captured by chance. In these cases, understanding becomes probabilistic and historical. It reconstructs events after the fact, from traces left behind. This reconstruction can be remarkably successful, but it is never complete. Details are lost. Resolution is limited. The past can be inferred, but not replayed. At very large scales, scientific understanding also encounters a kind of conceptual limit. The universe is not just large. It is dynamically evolving. Its expansion, composition, and geometry change over time. Models that describe the universe at one epoch may not apply at another. Understanding must account for this evolution, integrating time into its descriptions. This makes cosmology fundamentally different from many other sciences. There is only one universe to observe. There are no controlled experiments that can be repeated under different initial conditions. Understanding relies on consistency, on the coherence of multiple lines of evidence, and on the ability of models to explain a wide range of observations with a small number of assumptions. This uniqueness introduces an unavoidable uncertainty. Some features of the universe may be contingent, the result of particular initial conditions rather than universal necessity. Scientific understanding can describe what those conditions lead to, but it may never explain why they were what they were. This is not a gap waiting to be filled. It may be an inherent feature of a singular history. As scientific understanding stretches across scales, from the smallest interactions to the largest structures, it becomes increasingly clear that different kinds of limits apply in different regimes. At small scales, energy and disturbance dominate. At large scales, time and causality dominate. In between, complexity and emergence introduce their own constraints. What unites these limits is not obstruction, but adaptation. Scientific understanding does not insist on the same kind of knowledge everywhere. It adjusts its expectations. It learns where precision is possible, where approximation is sufficient, and where explanation must replace prediction. This adaptability is one of science's greatest strengths, but it also reveals something important about the original question. If scientific understanding were unlimited, it would look the same everywhere. It would deliver the same clarity at all scales. Instead, understanding changes character as it moves outward and inward, shaped by the structure of what it seeks to know. From here, the question of limits becomes less abstract and more grounded. The universe does not present a uniform surface to inquiry. It offers regions of transparency and regions of opacity, not because it is hiding, but because of how it is built. The next step is to examine what happens when scientific understanding confronts not just scale, but complexity itself. When simple laws give rise to behaviors that cannot be easily predicted or reduced, a different kind of limit emerges, one that challenges the relationship between explanation and prediction in a fundamental way. When scientific understanding turns toward complexity, it encounters a different kind of boundary, one that does not arise from distance, scale, or fundamental uncertainty, but from interaction itself. Complexity emerges when many simple components influence one another at the same time, creating behavior that cannot be traced cleanly to any single cause. Here, the laws governing the parts may be well understood, yet the behavior of the whole resists straightforward prediction. This is not because the system is poorly defined, it is because interactions multiply. In a complex system, each component responds not only to external conditions, but to the state of many others. Feedback loops form. Small changes can be amplified. Effects can circle back to influence their own causes. Understanding must now contend with a web rather than a chain. Weather provides a familiar example. The equations that describe fluid motion and heat transfer are known with great precision. They are deterministic in principle. Yet long-term weather prediction remains unreliable beyond a limited horizon. Tiny differences in initial conditions, differences smaller than any practical measurement can resolve, grow over time into entirely different outcomes. The atmosphere does not forget its uncertainties. It magnifies them. This phenomenon, often called chaos, reveals a subtle but profound limit. Even when the laws are known, and even when measurement is precise, prediction can fail. Scientific understanding can explain why prediction fails. It can map the sensitivity of the system. It can describe the statistical behavior of many possible outcomes. But it cannot track a single outcome indefinitely. This distinction matters. It shows that understanding and prediction are not the same thing. One can understand a system deeply while being unable to forecast its exact future. Scientific understanding adapts by changing its goals. Instead of asking what will happen, it asks what can happen and how likely different outcomes are. Complexity also appears in biological systems, where interactions occur across many levels at once. Molecules interact within cells. Cells interact within tissues. Tissues interact within organisms. Organisms interact within ecosystems. At each level, new patterns emerge that cannot be reduced easily to the level below. Life is governed by physics, but it is not described well by physics alone. Scientific understanding responds by developing new frameworks. Biology does not abandon chemistry, and chemistry does not abandon physics. But each level introduces its own concepts, its own regularities, and its own limits. Understanding becomes layered, with the different kinds of explanations coexisting rather than collapsing into one. This layering introduces a practical boundary. No single model can capture all levels at once without becoming intractably complex. Simplification is unavoidable. Choices must be made about which details matter. Understanding advances by focusing attention, not by exhausting description. As systems become more complex, computation enters the picture. Many complex systems can only be explored through simulation. Their equations cannot be solved exactly. Instead, computers step through their evolution, one increment at a time. This allows understanding to extend into regimes that would otherwise be inaccessible. But computation has its own limits. Simulations require time, memory, and energy. As the number of interacting components grows, the resources required to simulate them grow rapidly. Some systems become effectively impossible to simulate in full detail, even in principle, because doing so would require a computer as large and complex as the system itself. This creates a mirror of an earlier insight. Just as a model cannot contain every detail without becoming indistinguishable from reality, a simulation cannot fully replicate a complex system without matching its scale. Scientific understanding must again compromise. It seeks reduced models, coarse graining, and approximations that preserve essential behavior while discarding detail. In doing so, understanding becomes less about exact replication and more about pattern recognition. It looks for universal behaviors, phase transitions, and statistical regularities that appear across many systems regardless of their microscopic differences. This approach has been remarkably successful, revealing deep connections between seemingly unrelated phenomena. Yet, even here, limits remain. Some systems exhibit behaviors that are highly context-dependent. Small changes in structure or interaction can lead to qualitatively different outcomes. Understanding can classify these behaviors, but it cannot always predict which will occur in a given instance. This tension between explanation and unpredictability is one of the defining features of complexity. Scientific understanding can tell us why unpredictability arises. It can map the space of possibilities. But it cannot eliminate unpredictability without eliminating the interactions that give rise to complexity in the first place. As scientific understanding encounters these limits, it does not retreat. It becomes more nuanced. It learns to distinguish between what can be controlled and what can only be influenced. It develops probabilistic thinking. It embraces uncertainty as a feature of the systems it studies. This shift has consequences for how limits are perceived. A limit no longer looks like a wall beyond which nothing can be known. It looks like a change in the kind of knowledge that is available. Deterministic prediction gives way to statistical description. Exact trajectories give way to distributions. Control gives way to guidance. In this light, the question of whether human scientific understanding has a limit becomes richer. It is not a question about whether science will stop learning. It is a question about whether learning always takes the same form. Complexity shows that understanding can deepen even as certain ambitions are relinquished. As systems grow more complex, understanding becomes less centralized. It spreads across disciplines, methods, and perspectives. No single framework dominates. Instead, coherence emerges from the interplay of many partial views. Understanding becomes a network rather than a hierarchy. This networked character introduces another kind of constraint. Coordination itself becomes challenging. Integrating insights across domains requires communication, translation, and shared standards. Scientific understanding grows socially as well as intellectually. Its limits are shaped not only by nature, but by how knowledge is organized and shared. From here, the path forward leads naturally into the role of information and computation more explicitly. If understanding relies increasingly on data, models, and simulations, then the physical limits of information processing itself become relevant. The next stage of the question asks how far scientific understanding can extend when it is constrained not just by complexity, but by the fundamental costs of storing, processing, and transmitting information. As scientific understanding leans more heavily on data, models, and simulation, it begins to encounter limits that arise not from the phenomena being studied, but from the act of understanding itself. Information is not abstract. It must be stored somewhere, processed by something, and moved from place to place. Each of these steps is a physical process, governed by the same laws as everything else in the universe. This realization marks a quiet but important shift. Understanding is no longer just about observing and explaining. It is about computation. To understand a system increasingly means to calculate its behavior, to simulate its dynamics, or to analyze large volumes of data for patterns. Scientific insight becomes inseparable from information processing. Computation, however, is not limitless. Every calculation requires time. Every stored bit occupies physical space. Every logical operation consumes energy and produces heat. These costs are usually negligible in everyday contexts, but they become significant when understanding is scaled up to vast systems or extreme precision. Physics has revealed that there are fundamental limits to how efficiently information can be processed. There is a minimum amount of energy required to erase a bit of information. There are limits to how fast signals can propagate. There are bounds on how much information can be packed into a given region of space. These are not technological barriers waiting to be overcome. They are consequences of thermodynamics and relativity. This means that scientific understanding, when pursued through computation, inherits these limits. A simulation cannot run faster than the physical processes that implement it. A model cannot track more detail than memory allows. A dataset cannot be analyzed without dissipating energy into the environment. Understanding has a physical footprint. This becomes especially relevant when science confronts systems of extreme complexity. To simulate a molecule accurately may require tracking the interactions of many electrons. To simulate a living cell may require modeling countless biochemical pathways. To simulate a climate system may require resolving interactions across the entire planet. Each increase in fidelity multiplies computational demands. At some point, a simulation becomes so detailed that it approaches the complexity of the system it represents. This is not just impractical. It reveals a conceptual boundary. A model that includes every detail of a system offers no simplification. It ceases to be a model and becomes a duplicate. Understanding, which relies on compression and abstraction, disappears. This insight echoes through many areas of science. In physics, it appears in discussions of whether the universe itself could be simulated. In neuroscience, It appears in questions about whether a complete simulation of a brain would be necessary to understand consciousness. In climate science, it appears in the trade-off between resolution and scope. In each case, the same pattern emerges. Understanding does not scale indefinitely with detail. Beyond a certain point, adding more information does not clarify, it obscures. Scientific understanding depends on finding the right level of description, not the maximum one. Information theory provides a language for this balance. It distinguishes between signal and noise, between meaningful structure and random variation. Understanding grows when data can be compressed without losing what matters. When compression fails, it signals either that patterns are absent or that the wrong representation is being used. But compression itself has limits. Some data sets resist simplification. Some systems generate behavior that appears effectively random, even though it arises from deterministic rules. In these cases, scientific understanding shifts again, from detailed description to statistical characterization. This shift does not eliminate limits. It acknowledges them. It accepts that some information cannot be reduced further without loss. Understanding becomes a matter of describing distributions, correlations, and probabilities rather than exact states. As science increasingly relies on computation, it also becomes dependent on infrastructure. Data centers, satellites, supercomputers, and networks form the physical backbone of modern understanding. These systems require resources, maintenance, and coordination. Their growth is constrained by economics, energy availability, and environmental impact. This introduces a new layer of limits, one that is not purely physical but practical. Scientific understanding is embedded in societies. It depends on collaboration, funding, education, and trust. Even if no fundamental limit existed in principle, there would still be limits imposed by how knowledge is produced and sustained collectively. Yet even here, understanding has shown remarkable adaptability. Distributed computing, shared data repositories, and open collaboration have allowed science to scale beyond individual institutions. Understanding becomes a collective process, extending across continents and generations. This collective nature, however, introduces its own constraints. Coordination becomes complex. Specialization increases. No single person can grasp the whole. Understanding exists as a network of partial insights, held together by shared standards and methods rather than by unified comprehension. This raises a subtle question. If understanding is distributed, can it still be said to belong to humanity as a whole? Or does it fragment into pieces that no one fully holds? The limit here is not one of knowledge itself, but of integration. Scientific understanding continues to grow, but it grows unevenly. Some areas advance rapidly, fueled by data and computation. Others progress slowly, constrained by complexity or lack of access. The landscape of understanding becomes varied, with peaks of clarity and valleys of uncertainty. Through all of this, one theme remains consistent. Limits do not appear as abrupt endings. They appear as changes in pace, in method, in expectation. Understanding slows, redirects, or reframes itself in response to constraints, but it does not simply stop. At this stage, the question of whether there is a limit to human scientific understanding has become more textured. Limits arise from physics, from complexity, from computation, and from social organization. None of them alone end inquiry. Together, they shape its form. From here, The next natural step is to look more closely at how scientific understanding grows not just through methods and machines, but through people working together. How collaboration, specialization, and cumulative knowledge both expand and complicate what can be understood. That social dimension quietly determines how close science can come to any of its horizons. As scientific understanding becomes increasingly collective, its growth begins to depend less on individual insight and more on coordination. No single mind designs a particle accelerator, maps the genome, or models the climate alone. These achievements emerge from many people contributing small pieces, often without seeing the full picture. Understanding, at this stage, becomes something that exists between people rather than inside them. This collective structure has allowed science to grow far beyond the limits of individual cognition. Tasks are divided. Expertise deepens. Instruments become specialized. Knowledge accumulates across generations. A discovery made in one place becomes the foundation for work done elsewhere, years or decades later. In this way, scientific understanding becomes cumulative, building a shared scaffolding that no one person could construct alone. At the same time, this distribution introduces a new kind of boundary. As knowledge expands, it fragments, fields subdivide, languages become specialized, methods diverge. Two scientists working in different domains may share little common vocabulary, even though both contribute to the same overarching body of understanding. Integration becomes a challenge in its own right. This fragmentation does not signal failure. It is a response to complexity. When the world reveals many layers of structure, understanding must follow those layers. But it does mean that understanding becomes harder to hold together. Connections between domains must be actively maintained. Without effort, insights remain isolated. Scientific understanding relies on institutions to manage this complexity. Journals, conferences, standards, and educational systems provide shared reference points. They allow knowledge to be evaluated, transmitted, and preserved. But institutions also introduce inertia. Ideas take time to spread. Paradigms become established. Novel approaches may struggle for recognition. This dynamic shapes the pace of understanding. Progress is rarely smooth. It accelerates in some areas while stalling in others. Breakthroughs often depend not just on new data, but on changes in perspective, on the ability to see connections that were previously obscured by specialization. The social nature of science also ties understanding to resources. Large experiments require funding. Long-term observations require stability. Access to instruments and data is unevenly distributed. These factors influence which questions are asked and which remain unexplored. Limits arise not only from nature, but from circumstance. Yet, scientific understanding has shown a remarkable capacity to adapt socially. International collaborations form around shared goals. Data is increasingly shared openly. Computational tools allow researchers to build on one another's work at unprecedented speed. Understanding becomes more networked, more resilient. Still, the question remains whether this collective growth can continue indefinitely. As the body of knowledge expands, education becomes more demanding. Training a scientist takes longer. Mastery requires navigating an ever larger landscape of prior work. The threshold for meaningful contribution rises. This creates a subtle tension. Scientific understanding grows, but the number of people who can engage deeply with any given part of it may shrink. Expertise becomes narrower. Integration depends on translation between specialists. Understanding becomes layered not just conceptually, but socially. At the same time, science increasingly relies on automation. Data analysis, pattern recognition, and even hypothesis generation are assisted by machines. This extends collective understanding beyond human cognitive limits, but it also changes the nature of participation. Insight may emerge from processes no single person fully understands. This does not mean understanding is lost. It means it becomes distributed across humans and machines together. The boundary between tool and thinker blurs. Scientific understanding becomes a hybrid process, shaped by algorithms as well as intuition. This hybrid nature raises questions about ownership and comprehension. If a model produces accurate predictions but cannot be easily interpreted, is it understood? Science has traditionally valued explanation alongside prediction. As tools become more opaque, that balance is tested. Yet even here, limits do not appear as endings. They appear as choices. Science must decide what kinds of understanding it values, what trade-offs it accepts, and how it defines success. These decisions shape the trajectory of inquiry as much as physical law. At this stage, the idea of a single, absolute limit to human scientific understanding begins to dissolve. Instead, there are many interacting constraints. Physical laws shape what can be measured. Complexity shapes what can be predicted. Computation shapes what can be simulated. Society shapes what can be pursued and integrated. Understanding grows within this web of influences. It is not free to expand in any direction at any speed, but neither is it confined to a narrow path. It adapts, reorganizes, and finds new ways forward. From this vantage point, the original question can be approached with greater subtlety. A limit does not have to mean a stopping point. It can mean a horizon that moves as understanding itself changes. It can mean a boundary that defines the shape of inquiry rather than its end. To see this more clearly, the final step is to return to the question of what it means to understand at all. Not as an abstract ideal, but as a human activity unfolding inside a universe with structure, history, and constraints. Only then can the idea of a limit be understood in its full context, not as a wall, but as part of the landscape through which scientific understanding continues to move. Understanding, when looked at closely, is not a static possession. It is an activity, something that happens over time as patterns are noticed, tested, refined, and sometimes abandoned. It lives in the space between questions and answers, and it changes shape as those questions change. To ask whether there is a limit to human scientific understanding is therefore to ask whether this activity can continue transforming itself without reaching a final, fixed form. One way to approach this is to notice that scientific understanding does not aim to mirror reality in full detail. It aims to orient us within it. A theory does not reproduce the universe. It highlights relationships that matter for certain purposes. When those purposes shift, understanding shifts with them. This flexibility suggests that understanding is not something that accumulates until it is complete. It is something that adapts to context. This becomes especially clear when considering how science revises itself. Scientific revolutions are often described as moments when old frameworks are replaced by new ones. But in practice, change is rarely so abrupt. New ideas coexist with old ones. They overlap, compete, and gradually reshape the landscape. Understanding evolves more like an ecosystem than a straight line. In such an ecosystem, limits play a constructive role. They constrain growth in one direction and encourage exploration in another. When a method reaches its limit, new methods emerge. When a model fails, new questions arise. Limits, in this sense, are not endpoints. They are signals that guide adaptation. This adaptive quality is visible in how science responds to uncertainty. Rather than seeking to eliminate uncertainty entirely, scientific understanding often incorporates it explicitly. Probability distributions, confidence intervals, and error estimates become part of the description. Understanding deepens not by pretending uncertainty is absent, but by mapping its structure. This mapping allows science to operate effectively even in the presence of incomplete information. It allows predictions to be made cautiously, decisions to be informed probabilistically, and risks to be assessed realistically. Understanding becomes a way of managing uncertainty rather than abolishing it. Seen this way, a limit to understanding would not necessarily mean ignorance. It would mean a region where uncertainty cannot be reduced further without altering the nature of the question. Scientific understanding might reach a point where it can say everything that can be said in a given framework, even if that includes acknowledging what cannot be known. This idea challenges the common image of science as a quest for final answers. Instead, it suggests a process that continually refines the questions themselves. As understanding deepens, questions become more precise, more constrained, and sometimes more modest. The ambition shifts from knowing everything to knowing clearly what can and cannot be known. There is also a temporal dimension to consider. Scientific understanding unfolds over generations. It is shaped by historical contingencies, cultural values, and technological possibilities. What seems like a limit at one time may dissolve at another as new tools and perspectives emerge. Conversely, what seems open may later reveal itself as constrained. This temporal unfolding means that limits are not always visible from within the present moment. Some limits only become apparent after long exploration. Others are anticipated long before they are encountered. Understanding advances not by avoiding limits, but by discovering their shape. At the same time, the universe itself is not static. It evolves. Conditions change. Opportunities arise and fade. The expansion of the universe, the evolution of stars, and the emergence of life all shape what can be studied and when. Scientific understanding is embedded in this larger story. It unfolds alongside the phenomena it seeks to understand. This embedding suggests that scientific understanding may never reach a final resting point. Not because it is infinite in scope, but because it is always responding to a changing reality. New phenomena emerge. Old ones transform. The questions that matter evolve. Yet even within this openness, there may be enduring constraints. The speed of light, the uncertainty of quantum measurements, the irreversibility of entropy, the limits of computation, and the challenges of complexity all suggest that some aspects of reality resist complete capture. Understanding can approach these aspects, describe their boundaries, and work within them, but it may never dissolve them entirely. This does not make understanding fragile. It makes it resilient. By acknowledging limits, science avoids overextension. It maintains coherence by aligning ambition with possibility. Understanding remains grounded because it knows where it stands. From this perspective, the idea of a limit to human scientific understanding becomes less threatening. It does not imply that curiosity will be extinguished or that discovery will cease. It implies that understanding has a form, shaped by both human capacities and the structure of the universe. Understanding can continue to deepen even as certain horizons remain fixed. It can become more nuanced, more integrated, more reflective. It can learn not only about the world, but about its own methods and assumptions. In doing so, it gains a different kind of depth. This self-awareness is itself a product of scientific understanding. By studying how knowledge is produced, science refines its tools and clarifies its goals. Understanding becomes not just outward-looking, but reflexive. It learns from its own history. As this reflexivity grows, the question of limits shifts again. It becomes less about whether science will run out of things to discover, and more about how it will choose to define discovery. Will understanding prioritize explanation, prediction, control, or meaning? Different choices lead to different paths, each with its own boundaries. In this light, a limit is not a single line drawn across the future. It is a set of contours that shape the terrain of inquiry. Some paths rise steeply and then level off. Others wind slowly through complex landscapes. Still others open into unexpected clearings. Scientific understanding moves through this terrain not as a conqueror, but as a traveler. It learns the lay of the land by moving through it, adjusting pace, changing direction, and sometimes resting. The journey has no fixed endpoint, but it is not without structure. The universe does not promise to be fully transparent. It offers patterns, regularities, and surprises in unequal measure. Scientific understanding responds by becoming attentive, disciplined, and creative. It listens as much as it asserts. It adapts as much as it advances. As long as there are patterns to notice, questions to refine, and methods to test, scientific understanding continues. Its limits, wherever they lie, do not silence inquiry. They give it shape. If scientific understanding has a shape, it is shaped as much by restraint as by reach. Each time science learns something new, it also learns where that knowledge applies and where it does not. This awareness grows quietly alongside discovery, often unnoticed, yet it plays a crucial role in keeping understanding coherent. Without it, science would fracture under the weight of its own claims. One way this coherence is maintained is through the careful separation of questions. Science learns to distinguish between questions about mechanism and questions about origin, between description and explanation, between what can be tested and what can only be inferred. These distinctions do not weaken understanding. They protect it from confusion. By learning which questions belong where, science avoids forcing answers where none can be justified. This disciplined separation becomes especially important at the boundaries of knowledge. As scientific understanding approaches areas where evidence thins or uncertainty grows, it often slows down. Hypotheses become more tentative. Language becomes more precise. Claims are framed conditionally. This is not hesitation born of doubt, but caution born of experience. Such caution reflects an accumulated memory of past overreach. History offers many examples where confidence outpaced evidence, where elegant ideas collapsed under scrutiny. Scientific understanding carries these lessons forward. It learns that progress depends not only on boldness, but on patience. This patience allows science to remain open-ended without becoming unmoored. It accepts that some questions may remain unanswered for long periods, not because they are unimportant, but because the conditions for answering them are not yet in place. Understanding grows by waiting as well as by acting. there is also a deeper sense in which limits contribute to meaning. A universe that could be fully understood in every detail might leave little room for curiosity. Mystery, when it is structured rather than chaotic, provides a direction for inquiry. Scientific understanding thrives on this structured mystery. It is drawn forward by what is partially known and partially hidden. This balance between clarity and opacity gives science its enduring vitality. Each answer refines the landscape of questions rather than erasing it. Understanding does not collapse mystery into silence. It reshapes mystery into something more precise, more bounded, and more approachable. At times, the limits of understanding even become subjects of study in their own right. Science investigates uncertainty, chaos, complexity, and incompleteness not as failures, but as phenomena with their own structure. By doing so, it turns limits into objects of understanding. This reflexive turn is one of the most subtle achievements of scientific thought. It shows that understanding does not stop at the edge of what can be known. It extends to knowing where and why that edge exists. In this way, limits become integrated into understanding rather than standing outside it. As this integration deepens, the original question begins to shift once more. The question is no longer whether there is a limit to human scientific understanding in the sense of a final barrier. It becomes a question about how understanding relates to finitude. Can a finite process engage meaningfully with an indefinitely rich reality? Scientific understanding suggests that it can, precisely because it does not seek total possession. It seeks alignment. It asks not how to capture everything, but how to remain responsive to what is encountered. This responsiveness allows understanding to renew itself, even as certain horizons remain unchanged. The universe does not reveal itself all at once. It reveals itself through interaction, through constraint, through time. Scientific understanding mirrors this gradualness. It unfolds step by step, shaped by feedback from the world. Each step brings greater clarity in some directions and greater humility in others. Humility here is not resignation, it is calibration. It allows science to match its methods to its objects, to adjust expectations without abandoning ambition. Understanding grows more careful as it grows more powerful. This careful power is evident in how science handles extrapolation. Predictions are extended cautiously beyond tested regimes. Uncertainty is tracked rather than ignored. Models are stress-tested against extremes. Understanding advances by respecting the difference between what is known, what is likely, and what is merely possible. In doing so, science maintains a dynamic equilibrium. It pushes outward, but it also stabilizes inward. It expands the range of understanding while preserving its integrity. Limits serve as anchors as much as boundaries. From this perspective, the existence of limits does not threaten the future of scientific understanding. It shapes it. Limits define the contours along which understanding can grow. They prevent dispersion into unfounded speculation while encouraging depth where evidence supports it. As long as the universe continues to exhibit structure, regularity, and interaction, scientific understanding will continue to find purchase. It may not reach a final explanation of everything. It may never close the book on inquiry. But it can continue to refine its relationship with reality. Understanding, then, becomes less like a ladder with a top rung, and more like a landscape with paths that wind, branch, and sometimes converge. Some paths lead to clear vistas, others end in dense terrain. New paths appear as old ones fade. The presence of limits gives this landscape shape. Without them, understanding would be directionless. With them, it becomes navigable. Science does not need an infinite horizon to remain alive. It needs a world that responds, even if that response includes silence in some directions. And so the question of a limit to human scientific understanding settles into a quieter form. Not as a verdict to be delivered, but as an ongoing dialogue between curiosity and constraint. A dialogue that continues as long as there are minds attentive enough to listen to what the universe is willing to say, and careful enough to notice what it is not. As this dialogue between curiosity and constraint continues, something subtle begins to emerge. Scientific understanding does not simply move forward by accumulation. It deepens by learning how to listen. Each time inquiry presses against a boundary, the response from the universe is not a rejection, but a lesson in form. It teaches science how to ask better questions, how to phrase curiosity in ways the world can answer. This learning to ask is one of the least visible, yet most powerful aspects of scientific understanding. Early questions are often broad and imprecise. Over time, they become narrower, sharper, and more attuned to the structure of what is being studied. Understanding grows not only through answers, but through the refinement of questions themselves. When questions are well aligned with reality, progress can be swift. When they are misaligned, progress slows or stalls. This feedback shapes the evolution of science. Some lines of inquiry flourish because they resonate with deep regularities in nature. Others fade because the world offers no stable foothold for them. Limits, in this sense, act as filters, guiding attention toward what can be fruitfully explored. This filtering process is neither rigid nor final. New methods can open previously inaccessible questions. New perspectives can reveal structure where none was seen before. Scientific understanding is not confined to a fixed map. It redraws its map as it moves. Yet, even as maps change, certain features remain persistent. Causality, uncertainty, and irreversibility continue to shape inquiry. No amount of ingenuity removes the need for evidence. No theory escapes the requirement to connect with observation. Understanding remains grounded because it must. This grounding gives science its quiet authority. It does not claim certainty where none is warranted. It does not insist on completeness where only partial views are possible. Instead, it builds confidence through consistency, coherence, and humility. Understanding earns trust by showing its limits as clearly as its strengths. As the body of scientific knowledge grows, another pattern becomes apparent. Understanding often advances not by answering old questions, but by dissolving them. Questions framed in one conceptual language may lose meaning when that language is replaced. What once seemed fundamental becomes derivative. What once seemed mysterious becomes trivial. This transformation is not erasure, it is recontextualization. Scientific understanding rearranges the landscape of relevance. Some questions become obsolete because they no longer fit the structure of the world as it is now understood. New questions arise in their place, shaped by deeper insight. This continual reshaping suggests that limits to understanding may not be encountered all at once. They may be approached asymptotically as understanding grows more refined. Some questions may approach a point where further refinement yields diminishing insight. Others may remain perpetually open, generating new layers of inquiry without closure. In this way, Scientific understanding resembles a conversation more than a conquest. It responds to what the universe reveals, adjusts its tone, and continues. The conversation does not end because the universe does not exhaust its capacity to surprise. Even familiar phenomena can reveal new aspects when examined under new conditions. This openness does not imply boundlessness. Surprise itself has structure. Not everything is possible. Scientific understanding thrives within a constrained space of lawful behavior. The richness of inquiry arises from exploring that space, not from escaping it. As understanding matures, it also becomes more aware of its own assumptions. Concepts once taken for granted are examined critically. Definitions are sharpened. Categories are questioned. This self-examination prevents stagnation. It allows understanding to remain flexible even as it becomes more precise. The awareness of limits plays a role here as well. By recognizing where assumptions break down, science avoids building on unstable foundations. It learns to distinguish between what is fundamental and what is convenient. Understanding deepens by becoming more selective. This selectivity has an emotional dimension as well. There is a quiet satisfaction in recognizing that not everything must be known to be meaningful. Scientific understanding does not diminish wonder. It refines it. By clarifying what can be explained, it sharpens appreciation for what remains open. The universe, in this light, is not a puzzle to be completed, but a system to be engaged with. Scientific understanding is one mode of engagement, powerful but not exhaustive. It reveals patterns, constraints, and relationships that orient human thought within a vast reality. As long as this engagement continues, understanding remains alive. Its limits do not silence inquiry. They guide it. They provide resistance against which insight can form, much like tension in a string allows music to emerge. The question of whether there is a limit to human scientific understanding thus continues to unfold, not as a problem to be solved, but as a condition to be inhabited. Understanding grows by living within its constraints, learning their shape, and discovering what they make possible. Each generation inherits not only answers, but boundaries. Those boundaries become the starting points for new exploration. Understanding advances by stepping carefully up to them, pressing gently and listening closely to how the universe responds. And so the process continues, shaped by patience, curiosity, and respect for the structure of reality. Scientific understanding does not race toward an end. It moves steadily, attentive to both what is revealed and what remains just beyond reach, held in balance by the quiet knowledge that limits are not the end of understanding, but part of its enduring form. There is another way to feel the presence of limits in scientific understanding, and it appears when science turns its attention to itself. When scientists ask not only what the universe is like, but how we come to know anything about it, understanding gains a reflective depth. This reflection does not weaken science. It strengthens it by revealing the conditions under which knowledge is possible at all. One of these conditions is coherence. Scientific understanding depends on internal consistency. Theories must fit together without contradiction. Observations must align with explanations. When inconsistencies appear, they signal either error or incompleteness. Much of scientific progress arises from resolving these tensions, from finding frameworks that can hold more without breaking. But coherence has limits. As understanding expands, maintaining consistency across all domains becomes increasingly difficult. Concepts that work well in one area may not translate cleanly to another. Language that is precise at one scale becomes ambiguous at another. Understanding grows by partitioning reality into domains where coherence can be preserved locally, even if global unification remains elusive. This is visible in the structure of modern physics. Different theories govern different regimes. Quantum mechanics describes the very small. Relativity describes the very large. Both are extraordinarily successful where they apply, yet they resist seamless integration. Scientific understanding continues to explore ways to unify them, but the persistence of this gap suggests that coherence itself may have boundaries. These boundaries do not imply failure. They reveal the layered nature of reality. Understanding adapts by working within layers, respecting the conditions under which each description holds. A single, all-encompassing theory may be possible, but even if it exists, it may not eliminate the need for multiple perspectives. Understanding may remain plural by necessity. Plurality introduces another subtle limit. Different explanations can coexist without contradiction, each illuminating different aspects of the same phenomenon. A biological process can be explained in terms of chemistry, information processing, or evolutionary history. None of these explanations cancels the others. Understanding grows sideways as well as downward. This sideways growth resists simple measures of completeness. There is no obvious point at which enough explanations have been given. New perspectives can always reveal new connections. Understanding deepens not by converging on a single description, but by weaving together many. At the same time, this weaving requires judgment. Not every perspective is equally useful. Scientific understanding advances by learning which distinctions matter and which do not. This discernment is itself a form of knowledge, shaped by experience and constraint. Limits play a role here as well. When distinctions fail to yield predictive or explanatory power, they are set aside. Understanding refines itself by pruning as much as by adding. Growth is selective. As science continues to mature, it also becomes more aware of the difference between explanation and meaning. Scientific understanding explains how phenomena occur and how they relate. It does not prescribe values or purposes. This separation is not a weakness. It clarifies the role of science within a broader human context. Yet, even this clarification has boundaries. Scientific understanding can inform ethical decisions by describing consequences, risks, and trade-offs. It can illuminate what is possible and what is not, but it cannot determine what should be valued. That distinction marks a limit of scope rather than of depth. Recognizing this scope allows scientific understanding to remain focused. It prevents the overextension of explanation into domains where other forms of understanding are more appropriate. Limits, again, preserve coherence. There is a quiet maturity in this recognition. Science does not need to answer every question to be profound. Its power lies in answering certain kinds of questions exceptionally well, and in knowing which questions those are. As understanding continues to evolve, it carries this maturity forward. It becomes more careful with claims, more precise with language, more attuned to context. These qualities do not slow progress. They stabilize it. The future of scientific understanding will likely continue this pattern. New discoveries will open new domains. New technologies will extend perception. New theories will reorganize what is known. Along the way, new limits will appear, not as surprises, but as companions. These limits will not all be the same. Some will arise from physical law, others from complexity. others from the social and cognitive structures that support knowledge. Understanding will respond to each in its own way, sometimes by pushing through, sometimes by stepping around, sometimes by pausing to reconsider. What remains consistent is the posture of inquiry. Scientific understanding approaches the universe with attentiveness rather than force. It tests, listens, adjusts. It grows through dialogue with reality rather than domination of it. In this posture, limits are not adversaries. They are signals. They indicate where attention must shift, where methods must change, where expectations must be recalibrated. Understanding deepens by honoring these signals. As long as this dialogue continues, scientific understanding remains open-ended in practice, even if bounded in principle. Its horizons may not recede infinitely, but they are rich enough to sustain curiosity across generations. The universe offers a finite set of laws, but an inexhaustible set of contexts in which those laws unfold. Scientific understanding moves among these contexts, finding order, discovering surprise, and learning again and again how to see. And in that ongoing act of seeing, shaped by constraint and guided by curiosity, understanding continues, not toward a final answer, but toward ever clearer ways of asking what it means to know at all. There is a quiet continuity that runs through all of this, a thread that connects the earliest acts of noticing to the most abstract theories of today. Scientific understanding begins by paying attention, and it continues by refining that attention. What changes over time is not the impulse to understand, but the precision with which that impulse is guided. As understanding grows more precise, it also grows more selective. It learns that not every question is equally well posed, and not every curiosity can be satisfied in the same way. Some questions invite explanation through mechanism. Others invite description through pattern. Still, others invite acknowledgement of uncertainty. Scientific understanding becomes skilled at choosing the right response to each. This skill is not innate. It is cultivated through repeated encounters with resistance. When an explanation fails, when a prediction breaks down, when a model proves inadequate, understanding is forced to recalibrate. These moments of recalibration are often uncomfortable, but they are also generative. They reshape the boundaries of what science considers possible. Over time, this reshaping leads to a kind of quiet wisdom. Scientific understanding learns not only how to advance, but how to pause. It learns when to push harder and when to step back. It recognizes that some problems yield only after long preparation, and others may never yield at all. This recognition does not extinguish curiosity. It refines it. Curiosity becomes more patient, more disciplined, more attentive to detail. Understanding grows deeper not by accelerating endlessly, but by learning how to dwell with complexity. In this dwelling, science often finds that the most fruitful questions are not the largest ones, but the ones that sit at the edge of what is already known. These questions are specific enough to be testable, yet open enough to lead somewhere new. Understanding advances by exploring these edges, gradually expanding the territory of the known. The edges shift as understanding shifts. What once lay at the boundary becomes central. New boundaries appear further out. Limits, in this sense, are not fixed lines. They are moving interfaces between clarity and uncertainty. At the same time, some boundaries remain remarkably stable. The speed of light does not change. Entropy continues to increase. Quantum uncertainty persists. These features of the universe provide a kind of scaffolding for understanding. they anchor inquiry, preventing it from drifting into fantasy. Scientific understanding thrives within this scaffolding. It explores the space that the universe allows, learning its dimensions, its textures, its constraints. The richness of this space does not depend on infinite freedom. It depends on structure. Structure is what makes understanding possible at all. Without regularities, there would be nothing to learn from experience. Without constraints, there would be no way to distinguish signal from noise. Limits are not opposed to understanding. They are what give it form. This realization reframes the original question yet again. Asking whether there is a limit to human scientific understanding may be less about whether knowledge will end, and more about whether understanding will ever cease to be meaningful. As long as the universe continues to exhibit structure, understanding has something to engage with. Even if certain ultimate questions remain unanswered, scientific understanding can continue to deepen in other ways. It can become more integrative, connecting insights across scales and disciplines. It can become more precise, narrowing uncertainty where possible. It can become more reflective, clarifying its own assumptions and methods. Depth, here, does not require totality. It requires coherence. Understanding deepens when explanations fit together more smoothly, when predictions become more reliable within their domains, when uncertainties are better understood and communicated. In this sense, scientific understanding resembles a conversation that grows more nuanced over time. Early statements are simple and broad. Later ones are qualified, contextual, and carefully framed. The conversation does not end because it becomes more sophisticated. It becomes richer. The future of scientific understanding will likely continue along this path. New instruments will reveal phenomena previously hidden. New theories will reorganize existing knowledge. New forms of collaboration will reshape how inquiry is conducted. Along the way, limits will continue to appear, not as abrupt stops, but as invitations to adapt. Some limits will be encountered repeatedly, from different angles. Each encounter will add detail, sharpening understanding of why those limits exist and how they shape inquiry. Others will emerge unexpectedly, challenging assumptions and opening new directions. Through all of this, one thing remains constant. Scientific understanding is an activity carried out by finite beings within a finite universe. It is shaped by physical law, by cognitive capacity, by social structure, and by historical context. These shaping forces do not diminish its value. They give it character. Understanding does not need to be infinite to be profound. It needs to be responsive. It needs to remain open to revision, attentive to evidence, and aware of its own boundaries. When it does, it continues to grow in ways that matter. As the dialogue between curiosity and constraint carries on, scientific understanding maintains its balance. It neither claims final authority nor retreats into skepticism. It moves forward carefully, guided by what the universe reveals and restrained by what it withholds. In this balance, understanding finds its enduring strength. It is not defined by the absence of limits, but by its ability to live with them, to learn from them, and to let them shape a way of knowing that remains both humble and powerful, generation after generation. As scientific understanding continues to move forward, it also learns to slow itself down. This slowing is not hesitation, but calibration. It reflects an awareness that clarity often emerges not from rushing ahead, but from lingering with what is already partly understood. In these moments, understanding deepens by consolidation rather than expansion. Consolidation is an underappreciated phase of science. It is the period when ideas are tested across contexts, when methods are refined, when results are replicated and stress-tested. During consolidation, understanding becomes more reliable, even if fewer dramatic discoveries are announced. Limits play a role here by signaling where consolidation is needed before further progress is possible. This rhythm of expansion and consolidation suggests that scientific understanding does not advance uniformly. It pulses. Periods of rapid discovery are followed by periods of careful refinement. Each phase depends on the other. Without expansion, understanding stagnates. Without consolidation, it becomes unstable. The presence of limits helps regulate this rhythm. When a domain resists further penetration, science turns inward, strengthening what it already knows. It clarifies assumptions, tightens definitions, and improves methods. Understanding becomes more robust, even if it does not immediately become broader. This robustness matters because scientific understanding must endure. It is not enough for an idea to be exciting. It must survive scrutiny, application, and time. Limits ensure that understanding grows in ways that can be sustained rather than merely extended. There is also an aesthetic dimension to this process. Scientists often speak of elegance, simplicity, and coherence as virtues. These are not decorative preferences. They reflect a deeper alignment between understanding and structure. When a theory is elegant, it often means it captures a pattern with minimal excess. It respects the economy of nature. Elegance can signal proximity to a limit. As understanding approaches a boundary, it often becomes more compact. Redundant explanations fall away. What remains is a tight correspondence between principle and phenomenon. This does not mean the explanation is complete. It means it is well tuned. At the same time, elegance has its own limits. Not all phenomena yield simple descriptions. Some are inherently messy, shaped by contingency and history. Scientific understanding must learn to accept this unevenness. It cannot impose simplicity where none exists. This acceptance marks another form of maturity. Science learns to distinguish between complexity that can be reduced and complexity that must be described. It does not force one mode of understanding onto every domain. It allows plural approaches to coexist. As understanding becomes more plural, it also becomes more resilient. When one framework reaches its limits, others may still offer insight. The richness of scientific understanding lies not in a single path to knowledge, but in the interplay of many. This interplay becomes especially important at the frontiers of research, where evidence is sparse and uncertainty is high. Here, science advances cautiously, often exploring multiple hypotheses simultaneously. Limits are encountered frequently, but they are provisional. Understanding remains tentative, open to revision. In these frontier regions, the boundary between known and unknown is not sharp. It is a gradient. Scientific understanding navigates this gradient by assigning confidence, by ranking possibilities, by updating beliefs as new data arrives. Limits here are negotiated rather than imposed. This negotiation reveals another important aspect of understanding. It is probabilistic, not absolute. Scientific claims carry degrees of confidence that reflect the strength of evidence. As evidence accumulates, confidence grows. When evidence is weak, confidence remains low. Understanding is honest about this. Honesty about uncertainty is one of science's defining strengths. It allows understanding to grow without pretending to finality. It keeps inquiry open while maintaining rigor. Limits are acknowledged, not hidden. This openness also allows science to remain responsive to surprise. Unexpected results are not dismissed outright. They are investigated. Sometimes they reveal errors. Sometimes they reveal new phenomena. Either way, understanding grows. Surprise plays a subtle role in shaping limits. When something unexpected persists, it signals that existing frameworks are incomplete. Science responds by revising those frameworks or by developing new ones. Limits shift accordingly. This shifting does not imply that all limits are temporary. Some are persistent because they arise from deep features of reality. Others may recede as understanding evolves. Distinguishing between these kinds of limits is itself an ongoing scientific task. As time passes, scientific understanding accumulates not only knowledge, but experience with its own boundaries. This experience informs judgment. It helps guide future inquiry. It teaches science where effort is likely to be rewarded and where patience is required. In this sense, understanding becomes seasoned. It carries a memory of past successes and failures. It learns from its own trajectory. Limits become part of that memory, shaping expectations and strategies. This seasoned understanding does not diminish curiosity. It channels it. It encourages exploration that is ambitious but grounded. It fosters questions that are bold yet precise. It sustains inquiry over the long term. The idea of a final limit to human scientific understanding becomes less pressing in this context. What matters more is whether understanding can continue to refine itself, to adapt to new conditions, and to remain responsive to evidence. So far, it has. As long as scientific understanding remains embedded in this adaptive process, it does not need to outrun its limits. It needs to live with them intelligently. In doing so, it continues to illuminate the universe not as a fully transparent object, but as a structured reality that can be known in part, in depth, and with care. And within that careful knowing, shaped by both curiosity and constraint, scientific understanding continues its quiet work, unfolding across time, sustained not by the absence of limits, but by the way it learns to move gracefully among them. As this long arc of inquiry settles, one final clarification gently comes into focus. Scientific understanding does not move toward an ending in the way a task is completed. It moves toward orientation. It tells us where we are, how different parts of reality relate, and what kinds of questions remain sensible to ask from within the universe we inhabit. When we ask whether there is a limit to human scientific understanding, we are really asking whether orientation can ever be finished. Whether there comes a point where nothing new can be learned about how the world fits together. The history of science suggests something quieter and more subtle. Understanding does not close. It stabilizes, then reorganizes, then opens again along different lines. Some limits, once discovered, remain. The speed of light does not relax. Quantum uncertainty does not fade with familiarity. Entropy does not reverse its course. These limits become part of the grammar of understanding, shaping how explanations are formed and how expectations are set. They do not block inquiry. They give it structure. Other limits turn out to be provisional. They dissolve when new methods, perspectives, or connections are found. What once seemed unreachable becomes routine. What once required immense effort becomes accessible. Understanding grows not by denying limits, but by learning which ones are fundamental and which are historical. Over time, scientific understanding becomes more than a body of knowledge. It becomes a way of relating to reality. It teaches patience in the face of complexity, humility in the presence of uncertainty, and confidence where evidence is strong. It trains attention to notice patterns without forcing them, and to accept silence where no answer is available. In this way, the idea of an ultimate ceiling loses some of its urgency. A ceiling implies pressure from above, a sense of being contained. Scientific understanding feels more like movement within a landscape, guided by contours rather than blocked by walls. Some directions rise steeply, others level off. New paths appear where none were expected. Understanding remains finite in its expressions, but open in its practice. Each generation inherits a world that is partly mapped and partly unknown. The unknown is not an empty space waiting to be filled, but a structured frontier shaped by what has already been learned. Scientific understanding advances by meeting that frontier with care. What endures is not the promise of total knowledge, but the continuity of inquiry. As long as the universe continues to exhibit structure, regularity, and change, there will be something to understand. And as long as understanding remains grounded in evidence, disciplined by method, and attentive to its own limits, it will continue to deepen in ways that matter. So, the question of whether there is a limit to human scientific understanding does not resolve into a simple yes or no. It resolves into a recognition. Understanding is bounded, but not exhausted. It is constrained, but not confined. Its limits are real, but they are also generative, shaping a form of knowledge that is resilient, adaptive, and quietly profound. If this quiet journey brought you a moment of calm, a gentle like or a soft tap on subscribe truly helps keep this calm corner of the universe glowing. And tell me, where in the world are you listening from tonight? Rest well until our next quiet journey.